Bhavesh Chauhan, who is currently a postdoc at TIFR. So the title he will be talking about is Opportunities in Detecting Neutral Current Interactions of Neutrinos. So please give a hand to me to welcome our speaker Bhavesh Chauhan. Over to you.
Okay. So thank you, Deep. Thank you, Saurav, for inviting me for this talk. Uh, Today, the main focus of this talk, as it is, uh, as you can see through the title, is detection of neutral current interactions of neutrinos, and I'll, I'll try to make the aim is to motivate you into thinking that the neutral current channel is important, difficult to detect, but yet possible. So what is the entire, let me begin by asking what is the entire fuss about detecting neutral current interactions? So in this slide, I'm trying to compare charge current interactions versus the neutral current interactions. Uh, can you see my cursor?
Yeah,
Yes,
yeah,
we can.
yeah.
Great. Yeah. So in a charge current interaction of neutrino, uh, it is mediated by the charged gauge bosons W1, W plus, W minus. Uh, and because it's a charged current interaction, the outgoing particle, the outgoing lepton is a charged lepton. Okay. Here I'm assuming that it's a nuclear target. I mean, it's nucleus, it's some heavy nucleus or a nucleon. Uh, Typically, this channel is detected through the photons that are emitted by the charged lepton. So if it is energetic enough, then you see the Cherenkov radiation emitted by these electrons or charged leptons. And if it is a low energy electron, or not necessary, sorry, and if you're looking at a scintillator detector, then you'll see the scintillation light of this outgoing lepton. Typically, the momentum transfer in this process is rather small, and you can imagine that if you are colliding a ping pong ball with a bowling ball, the momentum transfer to the bowling ball is typically very small. So in analogous way, the momentum transfer, the energy transfer to the nucleus is rather small, and that's why it's very difficult to get any visible signal from the outgoing nuclei. So you only see the signal from the outgoing lepton. There are many advantages in detecting charge current interaction. First, since the momentum transfer is small, the outgoing lepton retains almost all of the energy of the outgoing neutrino. So therefore, it has large visible energy. The other thing is, again, because the momentum transfer is small, the energy that is carried by now I'll call it electron to be precise. Now, carried by the electron is more or less related to it's a one-on-one correspondence to the energy of the incoming neutrino. So, knowing the energy of the electron and the direction, you can completely reconstruct what the energy of the incident neutrino was. The other thing is there is a chance of, in Cherenkov detectors, you looking at the Cherenkov cone of the electron, you can reconstruct the directionality of the incoming neutrino. The other thing written here is tagging, which is what happens if you have a inverse beta decay like reaction, where the outgoing particle is a neutron, and you can detect the radiative capture of this neutron, and use that to tag the events and get rid of certain backgrounds. This is how charge current interactions are typically detected in scintillator or Cherenkov detectors. What about neutral current interactions? First of all, in a neutral current interaction, which is mediated by Z boson, the outgoing lepton is again a neutrino. It is very it is very rare that this outgoing neutrino will interact again inside your detector. So this neutrino practically escapes your detector without interacting again. Since neutrinos are electrically neutral, they will not emit any sort of Cherenkov radiation, uh, or they'll not produce any visible scintillation light as well. So the only bet of detecting this neutral current interaction is that you detect the scintillation or Cherenkov of the outgoing, hadrons. And as I mentioned earlier, this momentum transfer to the hadrons is typically very small, and thus this channel becomes extremely difficult to detect. The only advantage of trying to measure neutral current interactions is that this is sensitive to all flavors of the neutrinos. Whereas since we are talking about low energy neutrinos, because of the production threshold for muon and taus, more often than not, for neutrinos which are below 200 MeV, you are only sensitive to electron flavored neutrinos and antineutrinos. That's why so far in neutrino detection, whether it is large volume Cherenkov detectors such as Super-Kamiokande, or whether you're talking about scintillator detectors such as Borexino or Camland, you have been mostly sensitive to charge current interactions. And neutral current interactions have only formed a small background, which is, you know, which is not talked about often. So today we are going to talk about how we are going to detect this neutral current interactions and what are the possible ways, what are the possible, detection techniques that we can employ. We are going to take two paths to detection of neutral current. First path is through deuteron dissociation. People who know a little bit about neutrino detectors might remember the Sudbury Neutrino Observatory SNO, which used heavy water instead of normal water to detect the neutral current interactions of solar neutrinos. So, in similar spirit, we'll talk about deuteron dissociation as a means to detect neutral current interaction. The other possible channel, which we'll talk about later on, is the elastic scattering on protons. You see, uh, this channel can be detected through the scintillation of proton or through the capture of neutron, and this channel will be detected through the scintillation of the proton. I'll The first 40 minutes of my talk would focus on the deuteron dissociation, and in the later half I'll focus on the in the later last 10-15 minutes I will talk about this channel. So with this as a motivation of what is going to follow, let me begin my part one of the talk. But if you have any questions right now, I'll be very happy to answer them. Okay, so assuming there are no burning questions right now, let me begin with part one. In this in this talk, in this part of the talk, I'll focus on our recent proposal to develop a deuterated liquid scintillator, which is which can be built with technology completely available in India, which and we are trying with an emphasis on detection of supernova neutrinos. Okay, this is based on this paper, which has been recently accepted in JCAP, and my collaborators are Vasudev Das Gupta and Vivek Datar. The question which we are trying to answer is, what would happen if, let's say, tomorrow there is a core collapse supernova in our near our galactic center. Well, the large volume detectors such as Super Kamiokande, water Cherenkov detectors such as Super Kamiokande, would observe several thousands of events, whereas scintillator detectors such as Borexino and Camland would observe about several hundred of events. A large fraction of these events would arise from inverse beta decay, where an incoming antineutrino strikes a proton, either inside the carbon nuclei or the free proton, or the oxygen nuclei, produces a positron and a neutron. as mentioned earlier, this is mediated by charge current interactions. What happens to, what are our detection prospects for the other flavor of neutrinos, which is nu mu, nu tau, and the corresponding antineutrinos? These non-electron flavor of neutrinos can be detected via these three processes. First is through the scattering on electrons, but as compared to inverse beta decay, this cross section is about 2 orders smaller, so you barely get any events that you can use for reconstruction. The other possibility is that you look at the elastic scattering on protons, something that I mentioned earlier. But the problem is that the proton produces a scintillation light which is quenched, and that's why it's rather difficult to detect. This channel was proposed in Bekomfar and Vogel uh, as was proposed to detect the non-electron flavors in detectors such as Borexino. The other possibility is that incoming neutrino or antineutrino excites your carbon or oxygen nuclei such that, and later on, this carbon or oxygen nuclei de-excites by emitting photons. The problem is, in this channel, you can, the de-excitation is more or less monochromatic, so you don't expect, you are not going to get any spectral information about the incident neutrino. So question naturally arises is, how can we reliably detect neutral current interactions? So when I say reliably, I mean you should have large statistics. Also, there should be a possibility to, reconstruct the incident spectra. Okay, so as a small detour into history is what we are going to do now. The Sudbury Neutrino Observatory in Canada, it measured the neutral current interactions of solar neutrinos, which basically solved the solar neutrino problem. It was a heavy water based Cherenkov detector. So what it did was it detected the dissociation of deuteron. So deuteron is a bound state of a proton and a neutron. So with a binding energy of 2.2 MeV. So a neutrino which can transfer more than 2.2 MeV energy to the deuteron can actually break up the deuteron. So in this breakup, a proton and a neutron is produced. Since this was a Cherenkov detector and we are talking about low energy neutrinos, the proton is non-relativistic, so it does not emit any Cherenkov radiation. Whereas this neutron, after scattering with the nuclei in your detector, gets thermalized and eventually gets captured on a deuteron, or in that case oxygen nuclei as well. So it gets captured on the deuteron, and it emits a monochromatic photon of 6 MeV or so. This 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 photon, this gamma photon, is then detected by in PMTs surrounding your detector material. So counting such monoenergetic protons, you can get a count of what is the total number of solar neutrinos. Clearly, there is no possibility of getting spectral information from this photon, because whatever initial energy this neutron carried, it got this that information was lost during thermalization. So this channel in snow especially, you could not detect you could not reconstruct the incident spectrum. So let us ask ourselves, what are the challenges that you would face if you want to build a snow-like detector today? First of all, the very first challenge is that the heavy water is extremely expensive, and it's not like you can go and buy heavy water because of nuclear treaties. It is more or less unavailable. For snow actually borrowed the heavy water from the Canadian government, and at the end of their operation, they had to return the heavy water to Canadian government. So heavy water is expensive. Deuterated stuff is expensive, and it is unavailable. The other problem is, since this neutron had to be, it thermalized and the thermalization length, the path length of the thermalization was about a few meters or so. A lot of these neutrons actually escaped the detector. So the neutron capture efficiency, especially in the first phase of snow, was really small. Later on, dopants such as uh, chlorine and tritium were added to the detector to enhance this neutron capture cross section, but we'll not talk about it. So the neutron capture efficiency was small in a purely deuterated detector. The other problem was, since this was a it was a Cherenkov detector, it had large thresholds. As mentioned earlier, proton was undetected, and such a channel did not carry any spectral information. So how are we going to solve this problem? First, India is one of the largest manufacturer of heavy water in the world, and our private conversations with heavy water board suggest that they can manufacture or provide us with uh, the required components at you know at reasonable cost. So India can manufacture required amounts of deuterated compounds. Now, to enhance the neutron capture efficiency, we simply add gadolinium. So this is something that Becom and Baggins had proposed earlier, and this is something that Super Kamyokande is doing right now. And the problem of large thresholds and blah 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 is resolved if you have a scintillator detector. Okay, so we propose a kiloton scale deuterated liquid scintillator in which you have added gadolinium, which is instrumented with PMTs and which can be used to study low energy neutrinos, especially through the neutral current channel. Okay. Although the main purpose of such a detector would be to study low energy atmospheric neutrinos and solar neutrinos, in this talk I'll focus on the detection of supernova neutrinos. Since we are trying to build a case, we'll not go into a lot of details of what the supernova neutrino flux looks like, and just assume that the supernova neutrino flux follows a simple profile, uh, and people who know about this will immediately realize this is a profile with pinching factor of 3. uh, this is extremely model dependent, and we for our preliminary estimates we take two different fluence models with average energies of the three flavors, higher in the optimistic case and lower in the conservative case. So these are the two fluence models that we consider. Now this this is the flux of the neutrino that is produced in supernova, just outside the neutrino sphere. So it will undergo many flavor conversions before it reaches Earth. To capture the effect of this flavor conversion, we'll assume two fiducial scenarios, where first is of flavor equilibrium, where we just assume that all the flavors have equilibrated within themselves, and the flux at Earth is the average flux of the three flavors. And the other scenario where we don't assume any oscillation. The reality In reality, the flux will be somewhere between these two scenarios. So we just take these two fiducial scenarios and provide our estimates. Okay. So what are the interactions and detectables in your detector? These are the four interaction channels, actually three, through which we propose the detection of supernova neutrinos. First is the neutral current channel, in which neutrinos and antineutrinos would dissociate the deuteron and producing a neutron and a proton. And the two charge current interactions, where an outgoing electron or a positron is produced. In case an electron is produced, it is accompanied by two protons, and if a positron is produced, it is accompanied by two neutrons. So you see, all these three channels, all these three flavors of supernova neutrinos have very different signatures in your detector. As mentioned earlier, the outgoing neutrino cannot be detected. The electron and the positron and the proton is detected through the scintillation, whereas the neutron is thermalizes and is captured in your detector. Let's look at what the neutral current interaction would look like. So an incoming neutrino breaks up the deuteron. The outgoing neutrino does not give any signal. Outgoing proton produces a scintillation light, and this neutron gets scatters in your detector and gets captured on gadolinium. Okay, so we see that through this channel you'll get in a kiloton of a deuterated liquid scintillator, you get more than 400 events for the high fluence scenario and more than 300 events for the low fluence scenario. Since this is a neutral current channel, it does not depend on the uh, flavor conversion scenario. So the predictions for no oscillation and flavor equilibrium scenario is the same. Well, even though this is not the main focus of this talk, in charge current interaction channel, you also get a large number of events, more than 100 events for each channel. I would like to point out here that this channel mu e, about getting about 170 events is it's very important because the only other detector in the world that is going to detect mu e is JUNO, which has comparable sensitivity would be DUNE. So this a DLS would be not only a very good neutral current detector but also a mu e detector. Okay.
So
Now,
I have
yeah,
a nice question that
yeah.
you said that neutron is captured in GD, but neutron itself can decay. So that decay, will that affect the process of capturing? So there is some
So what is
probability that it
the
can decay.
yeah,
So
definitely
so
neutron decay is possible.
yeah,
So do you know the lifetime of the neutron?
I think that is 180 seconds. I think.
Exactly.
Yeah.
So that's what it is. The neutron
Sorry,
gets
100 or so,
captured.
880 seconds. Sorry,
Yeah, yeah,
880 seconds.
it's much larger.
Yeah.
The neutron gets captured at the time scales of nanoseconds.
Okay. 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 Okay.
So
That's negligible then.
yeah, so the neutrons don't survive long enough for it to be for it to decay.
Okay. Okay. Go ahead.
Okay, I said nanoseconds. That is slightly wrong. It is around microseconds, few microseconds, few tenths of microseconds.
Okay. Okay.
But still,
Hmm.
that tells you that
Hmm.
neutron decay is negligible.
Hmm.
Okay, now that I have convinced you that you will get a lot of events, let us also look at the spectrum of the events. Okay, if I want to look at the spectrum of events, because looking at these spectrum is will be used to reconstruct the incident spectrum. So you immediately encounter two problems. First, as I mentioned earlier in the very beginning, the momentum transfer to the hadrons is very small. The other problem is something known as quenching. So what happens is that the if you start if you have a proton with kinetic energy, let's say a few MeV, not all of this energy is converted into visible light. Only a fraction is converted into visible light. And this is what that fraction looks like. So you can see the fraction ranges from somewhere around 10% to around 50% at higher energies. So you see, but there is one more thing, that the amount of quenching is, so there is a one-to-one correspondence between the quenched scintillation light and the initial kinetic energy of the proton. So quenching, even though it's problematic, but it can be inverted. So as such, it's not that big of a problem. The bigger problem is that because of this quenching, a lot of these higher energy protons get converted into lower energy protons, lower energy visible light, which is below the threshold. So that is where quenching hits you hard. Okay, so this is what so we've computed the differential cross sections and all these things using pi endless EFT and all. If you're interested, we can get into the details of that. But so you see, without quenching, you would have expected the proton spectrum to look like this. But because of quenching, there are almost negligible, very small number of protons at higher energies, and there is a threshold of 200 keV coming from carbon 14 decays inside your detector. So we our estimates are that you will get, for a high fluence scenario, you'll get about 84 protons which are above threshold. So 84 is still a good number. So using these 84 protons, you can more or less reconstruct the total neutrino spectrum, and using charge current interactions, this is what the spectrum would look like. You can reconstruct the nu e and nu e bar spectrum, and you can statistically subtract this to get the overall spectrum of non-electron flavors. So since in the same detector you can detect the neutral current, electron charge current, and anti-electron neutrino charge current interactions, within the same setup you are able to reconstruct the non-electron flavored neutrino spectrum. So this is a advantage of DLS that no other detector in the world would have. Okay, so the mini summary to motivate most of you is that a
Bhavesh,
kiloton scale, yeah,
sir,
hello, yeah, sorry, I can't hear you.
Uh,
yes, I don't know what is fluence. Uh,
Fluence is a time integrated flux. So we are not interested in the time variation, like in the 10 seconds of 10 second of the time interval, how the spectrum changes, but we look at the aggregate or the total spectrum in that 10-second window. So high flux is what you should think of. Fluence is just time integrated flux.
okay, okay.
Okay, so a mini summary: a kiloton scale DLS, and with an emphasis on some that it can be completely built and developed with technology that we already have in India, will observe a significant number of events as well as the spectrum of events from all the three flavors of supernova neutrinos. So this is something that this should motivate and excite uh, some of you. Okay, now I'll just give you a small analogy with cricket if you are if you're interested. A DLS is kind of like a hybrid detector between a snow and a borexino. So since I'm running slightly short on time, I will not delve into that. But it's basically it borrows some of the good things from borexino. It borrows some of the good things from snow, but still there are some deficiencies which we can talk about at the end. Okay, so more or less I have conveyed what I wanted to say today. So but we are going to take a small but a very important detour into secondary interactions. So in case you don't follow this, it is perfectly fine. You can forget about this part because these are some details, but it's I find it to be one of the interesting work that I have done, so I'm going to talk about it. Okay. So as I mentioned earlier, the final state protons will scintillate, and they travel about zero point 0.1 mm inside your detector. Whereas the neutrons, they will undergo secondary interactions. First, they'll elastically scatter off the deuteron and the carbon nuclei in the detector. The other possibility is that they'll get radiatively captured. Basically, they get captured on the carbon nuclei, excited, and a gamma is a MEV scale photon is released. The other possibility is that if these neutrons carry enough kinetic energy, they can break up the deuteron as well. Now you see, deuteron breakups are a problem because they kind of form the, since if you do not detect this neutron again, it goes on and thermalizes. Uh, this practically looks like a neutrino breakup of a deuteron. So deuteron breakups, if they are happening at sufficient rate, would form the background. Okay. So how do we analytically so we want to get an analytic or rough approximate estimate of what would be the magnitude of these interactions. So what we compare are, inspired from those of you who are familiar with cosmology. What we are comparing are interaction rates. Okay, so what we find is that high energy neutrons, and so this is these I'm showing in this plot various interaction rates at any given energy. Whatever is the highest interaction rate will dominate your interactions. That's what you should think. So you see, and the other thing is, as as this is also a plot in time, in a sense that a neutron that is somewhere over here around 10 MeV, in interactions it will lose energy and slightly follows, keeps on lowering its energy. So a high energy neutron will undergo elastic scattering on deuteron and carbon. It will lose energy, and you'll see that, at the end of its cycle, it will get captured on gadolinium. If there was no gadolinium, it would get captured on uh, a deuteron or carbon. Okay. Also, look at this. The breakups that I was talking about are not important. We'll show this quantitatively as well. So you can do following rough estimates that the number of elastic scatterings is roughly 30 to 35 for MeV scale neutrons. And if you don't add gadolinium, the neutron would undergo around 3000 scatterings before getting captured. With gadolinium, it is captured immediately. So without gadolinium, the capture time of the neutron is around 20 milliseconds. So this is a problem, because you see, you're expecting around 600 events in a 10-second window. So if the neutron is captured around with a 20 millisecond window, it becomes very difficult to tag the interactions. However, if you add gadolinium, the capture time reduces to around 50 microseconds, mostly coming from the thermalization time. And at this with this time scales, it is easy to tag the neutrons. So this is the reason why from the very beginning we are saying that we are going to load the scintillator with gadolinium. Okay. Now, this is slightly more detailed. The point of this is that the breakups are not important. I can explain this later on, but breakups are not important. The only thing that the secondary interactions where is going to hit you hard is, you see, in a neutral current interaction, the proton is produces a scintillation. The first interaction of this neutron on the deuteron, the elastic scattering can produce a scintillation signal through the deuteron as well. You see, deuteron is what? Proton and neutron. So it is electrically charged. So a recoil to the deuteron is going to produce a scintillation signal which is detected. We see that the time separation between these two signals will be of the order of a few nanoseconds. So if your detector has a timing resolution which is better than a nanosecond, not unprecedented, we already have picosecond detectors. If you have nanosecond resolution, then you will be able to segregate the proton scintillation and the deuteron scintillation in time. However, if you don't have this such a nice timing resolution, then these two signals will overlap, and it results in a deterioration of your energy resolution at higher energies. So this is why I said earlier that this is the whole point of why we talk about secondary interactions in a way. Okay, and this is going to hit you only for, it is important, and it is problematic only for neutral current interactions. These are not important for charge current interactions, because the scintillation from the electron or positron is going to overwhelm any scintillation signal from the hadrons. So these are not important there. So coming to a summary of part 1, deuterated liquid scintillator is a promising candidate for detecting neutral current interactions of low energy neutrinos. The fact that you end up with more particles in the final state as compared to ordinary detectors, uh, they can help you in tagging and mitigating backgrounds. We have shown that for a typical galactic supernova, you would observe more than 400 neutral current events, about 200 NUI events, which is, which no other detector other than DUNE can see, and some 100 NUI bar events. These NUI bar events are going to help you with your overall calibration with other detectors, because Super K is going to see some thousands of these CC events, so we don't discuss this channel in detail. So we talked about how the quenched scintillation from the proton can be used to reconstruct the spectrum of non-electron flavor neutrinos. If you have nanosecond timing resolution, the secondary scintillations can be identified. Otherwise, you just have some deterioration of energy resolution. And as happened with the solar neutrino problem, the measurement of neutral current interaction will provide you with an overall normalization of the supernova neutrino flux. So that is something that is going to aid in our understanding of flavor conversion scenarios. So before I move on to part 2, if there are any questions regarding this, I'll be very happy to answer. Okay, so if there are no questions about this, I'll move on to the second part of my talk, which is about atmospheric neutrinos, which scatter with protons in JUNO. Okay, so first of all, atmospheric neutrinos are produced in your when cosmic rays interact with the Earth's atmosphere. The water chemical detector Super K has already measured the flux of neutrinos between 100 MeV to 10 TeV using charge current interaction. The threshold of 100 MeV is for NUI and NUI bar, whereas for NUI and NUI bar, the threshold is around 200 MeV, coming from the Cherenkov threshold of neutrons. The neutrino proton elastic scattering was proposed for Super Kamiokande by BCom, whereas for scintillator detectors such as Borexino, it is a small background. The JUNO is an upcoming large volume liquid scintillator detector, which with a potential mass of around 20 kiloton. So what we are going to do is we are going to forecast the signal and background for the neutrino proton elastic scatterings at JUNO. Okay. So the spectrum is very well understood. The cross section is given by standard model interactions. So the event rate is very well understood in the event rate for the neutrino proton elastic scattering is very well understood, and this is what the spectrum would look like. The main error bars on this comes from the uncertainty in the neutrino flux. And you see, there is a reason why I have divided the spectrum into 3 components. First is the neutrinos, atmospheric neutrinos below 100 MeV. You see that below 100 MeV there is a large uncertainty in the predicted flux at JUNO. So most of it, and the other thing is that most of these events are below 10 MeV, where there are lots of backgrounds. The other part of the neutrino flux is between 100 and 200 MeV, and the last part is the tail of the neutrino spectrum, about 200 MeV. Since the flux falls as with a spectral index of 2.7 and the cross section is rising with the spectral index more than 2, what happens is that the contribution of neutrinos above 200 MeV is more or less flat in this regime. So if you can detect the slight upturn of this wind event, then what you are actually detecting is the neutral current interactions of neutrinos between 100 to 200 MeV. As I mentioned earlier, in this range, the Super K has only measured NUI. because super K is charge current interactions, and it is the muon production threshold is about 200. So measurement, so this, if you can detect this upturn of events, what you are practically measuring is the yet undiscovered, unmeasured flux of new mu's in this energy. Of course, what the statistically subtract mean, but that's a challenge for future. Okay, what are the major backgrounds that So this was about the signal. Now let us talk about the backgrounds. The major backgrounds come from comes from muon spallation. So high energy muon, which is typically produced in cosmic ray interactions with neutrinos, cosmic ray interactions with the atmosphere. This high energy muon will propagate inside Earth, all the while losing energy, and it will survive. If it survives the Earth's overburden, it can enter your detector. Now, because of this muon is highly energetic, it will lead to a lot of neutrons, gammas, E plus, E minus, pions, and a plethora of particles in its along its path inside your detector. So this is a shower of particles by a cosmogenic muon. These neutrons and these gammas then interact with the carbon nuclei in this track, along this track, and produce heavier isotopes. Okay, these isotopes will then eventually undergo beta decays, and the the electrons or positrons which are produced in this beta or beta plus minus decays, they will produce a scintillation signal, which you will not be able to differentiate from the scintillation from the neutrino interaction with protons. Okay, so this is known as the cosmogenic isotope background. For JUNO, it is estimated that the muon rate is around 3 Hz, basically 3 muons per second, and the average energy is around 215 G. Okay, so this is practically the list of all the isotopes that is produced in JUNO, and this is what the spectrum. Just take these isotopes, multiply with the spectrum, and you'll see that this is what the spectrum of event looks like. I've also overlaid the differential event spectrum from the Newton ES, elastic spectrum. You'll see that below this around 16 MeV in visible energy, you are hit with a wall-like background which is difficult to reduce. Nevertheless, we'll try. So this is how a cosmic muon veto is done. Every time you identify a muon track, around the muon track for a radius of 3 meters, you shut down the detector volume. Okay, you just stop. You just don't collect the data from. Just discard the data from this cylindrical volume. Okay, for how long? For a time of t, what we are calling is delta t veto. For two different choices of veto, what we are seeing is that the threshold can be lowered from somewhere around 16 MeV to something around 14 MeV. And we also point that this does not result in a very catastrophic destruction of your dead time. What I mean is that for delta t veto of 2 seconds, you end up losing only 10% of your exposure. Okay, if you keep on increasing delta t veto, the decrease in exposure is much larger, and you don't get a lot of events by lowering threshold. So somewhere between 1.2 seconds and 2 seconds is the sweet spot for the muon veto. Okay, so with this veto, you can actually lower the threshold to about 14 MeV. And for all our analysis, we assume that there is a wall-like threshold at 15 MeV, and below that, the cosmogenic isotope background will dominate. Remember, this is a log scale. So the other possible background is when an atmospheric neutrino can knock out a proton from the current. Okay, so I'm not going to talk about this in detail. Just I'll mention that these predictions were recently computed, and we just take their results with appropriate scaling. Okay, so this is a preliminary result, which is about the forecast for June. So the neutrino carbon events are about a factor of 2 larger than the neutrino proton elastic scattering events. Uh, these are the uncertainty in the new PES is relatively small, but the neutrino carbon prediction depends a lot on which Monte Carlo neutrino generator you are using, as well as certain properties of the nuclear structure. So this is something that is not known, and this is something that in future with more experiments we'll be able to figure out what are some of these parameters, and we can nail down some of the predictions. Okay, with this we kind of estimate that in 5 to 10 years JUNO will be able to establish the existence of new PES at 3 to 5 sigma level as well. Okay, so far so good. This is a prediction for um, an upcoming detector, but how can we use this to constrain new physics scenarios? So there is some sensitivity to new physics. Uh, so just for an example, we consider monochromatic flux of boosted dark sector particles on Earth. We consider two different scenarios. First is a heavy mediator, the other is a light mediator kind of scenario. Light being something which is below 100 MeV. And we consider two current interactions, which is like vector or axial vector interactions. So, and this is what the sensitivity to the new physics looks like. Well, though, so this is a model independent analysis. The only thing you can constrain is a product of the the flux normalization and the G effective. G effective is basically telling you about what are some of the parameters of basically telling you about what is the strength of the interaction. And you'll see that this is the parameter space that can be excluded from JUNO. I've also shown in light shaded region the parameter space that is already excluded from CAMLAN data. So you'll see that JUNO can do an order of magnitude better than CAMLAN within 1 year. Okay, now how to convert this very useless looking plot to something more useful? We can consider, I'll give you two examples. First is an example where you have a galactic dark matter which is annihilating into sterile neutrinos. These sterile neutrinos have very small mixing angle with neutrinos, so basically there is no conversion. And but these sterile neutrinos can interact with protons through some light mediator like scenario. Now, this is something that I've cooked up. You'll see that this is what the parameter space of sigma v versus m chi looks like, and CAMLAN data already rules out a large fraction. Below this you have an overabundance, so that's not, this region is also ruled out. And if JUNO with 1 year of data taking can basically exclude almost all of the parameter space for this sub G with dark matter scenario. Okay, the other, so as I mentioned here in this slide that you're basically sensitive to production times detection. Here I have mentioned a scenario where the production and the detection happen through different interactions, and that's why you have a lot of free parameters hanging around, such as effective coupling or something. Okay, but let us come to a scenario where the production and detection happen through the same new physics scenario. So this is the scenario of boosted dark matter, where a high energy cosmic ray interacts with a galactic dark matter particle, and kind of gives it a kick. Because this dark matter particle now has much larger kinetic energy, while interacting with protons in the detector, it will leave a large visible energy in your detector. So this is the scenario of boosted dark matter. You only have one free parameter, which is the cross section between the proton, which is the cosmic ray as well, and dark matter, and the dark matter mass. At higher energies, at higher MK, the mass of the dark matter, you have limits from direct detection such as crest. At below 1 MeV, you have problems with cosmology, basically BBM ineffective. And at very large cross sections, the xenon 1T data already rules out. The sensitivity of JUNO was projected in Capello and Decom, and this dotted line is what they obtained. But since now we know what the spectrum actually looks like, and we know that there is a threshold of 15 MeV. If you consider this, you'll see that the sensitivity to JUNO basically drops by one order of magnitude below 100 MeV. So as opposed to what Capello and Becom had projected. Uh, so so this is what an important application of what we have done is. So this is my quick summary of part 2, that the neutrino proton elastic scattering is a complementary channel to detect atmospheric neutrinos. The event rates are very well predicted within standard model. We have discussed what the event spectrum looks like as well as what are the backgrounds. The lower energy threshold is determined by the decay of cosmogenic isotopes, and we estimate the threshold to be around 16 MeV. And we find that with a very aggressive beta, we can reduce this threshold to be around 15 MeV. Um, the neutrino proton signal is about a factor of 2 smaller than the neutrino carbon background, and with a slightly larger exposure of 5 years or 10 years, the JUNO should be able to identify nucleus at the level of 3 sigma or 5 sigma. We also show that detection, once this channel is detected, you can put competitive limits on certain new physics scenarios which are rather difficult to detect in other detectors. So that's all, folks. Thank you.
Okay, thank you, Bhavesh, for your nice talk. So now, any questions and comments on his talk? So let me begin with one question. So,
Mhm.
uh, whatever you have talked that during the neutrino detection, so we cannot measure the mass or any some mixing angles, and some microphysics quantities in this process.
Okay. So
Can we
first,
do
let's
that?
come to mass. We are talking about neutrinos, which are, in case of supernova neutrinos, the average neutrino energy is around 20 MeV. And for atmospheric neutrinos, we are talking about neutrinos which are above 100 MeV in energy.
Yeah.
So it is very difficult to talk about neutrino masses there. Neutrino masses can be seen through, in oscillation physics.
Yeah.
Right? Now, if you remember what we have done in our paper is, we have just, sorry, let me just, yeah, the neutrino oscillation physics, which depends on the oscillation parameters, the mixing angles, the neutrino masses, and everything. All this will determine what exactly is the scenario between flavor equilibrium and no oscillation. Okay, look at this plot. Okay, you have a prediction for flavor equilibrium and you have a prediction for no oscillation scenario. Depending on what your survival probability is for this channel, which is also typically energy dependent, the actual the realistic expectation will lie somewhere in between these two scenarios. And this is where you'll start becoming sensitive to the neutrino parameters, mixing and mass parameters, but not in neutral current interactions, because neutral current channel is sensitive to the total number of neutrinos, right?
Hmm.
So oscillation will not be important for neutral current channel.
Okay.
So that's why through neutral current channel you will not be getting any, you will not reconstruct any mass and mixing parameters.
Okay. So another question that in the some of your channels there are some 2 to 3 processes. So
Yeah.
so which you said that uh, that is important to uh, 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 dissociate from the background. But those channels should be subdominant due to phase space suppression, isn't it? That you are considering 2 to 3 processes.
No, so the kind of, you're, first of all, you're right that since this is a 2 to 3 process, there is a quote unquote phase space suppression, but uh, compared to what?
Because there are.
There are no analogs of these channel in other detectors, right?
Hmm,
What is the comparative 2 to 2 process that you're talking about? For example, you're right that, for example, let us look at this process, the last process. The comparative 2 to 2 process would have been a neutrino interacting with proton and producing a positron and a neutron, right?
hmm,
So this is the inverse beta decay channel. Sorry, that is the inverse beta
yeah,
decay
yeah,
channel,
yeah,
and this is the neutrino interaction on deuteron. It has a threshold of around 4 MeV, and you're right that the cross section for this process is about a factor of 10 smaller than the cross section for the inverse beta decay.
yes,
So there is, so this is comparatively small. But now look at what is happening. In inverse beta decay, you are going to look at the scintillation from electron, sorry, the positron, and you will use the neutron to tag these events.
okay,
Okay, but in this channel, you have an additional neutron
hmm,
which will provide you, a triple coincidence tag, which is not going to happen in any other process, right? There are
yeah,
no natural processes that result in E plus and two neutrons.
yeah. So the momentum distributions would be different from the other processes of.
Yes, of course.
Yeah.
So look at this thing. Uh, in 2 to 2 process, the kinetic energy of the proton would be, kind of spiked
Hmm,
for a given neutrino energy.
hmm,
But here you end up with a distribution. With the peak, that is something that you can analytically determine.
okay.
So that is why this is also a challenge in reconstruction. Since you have three body final state,
Hmm,
there is no one-to-one correspondence between the kinetic energy of the proton and the kinetic energy of the incident neutrino.
I see.
So this is something that you have to solve by simulation,
Okay.
just like Ice Cube does at high energies.
And another question that you talked about the thermalization of the neutrons. So
Yeah,
that so thermalized with what? That the deuteron with.
with the detector medium, which is assumed to be at room temperature.
Oh,
So this is the Tn thermal. This is the kinetic, which is typically taken to be around 0.025 eV.
okay, okay, okay,
So basically, high energy neutron thermalizes to with the temperature of the detector.
okay, okay. Thank you very much. So
Yeah.
any other questions from the audience? So if not,
No.
let me thank Bhavesh once again. So can you just share your slides with us in via email? So
Yes, sure. Yeah,
that would be
sure,
helpful for us, and I will let you know
sure.
when I would upload this to YouTube. So,
Okay,
so
great.
thank you
That
very
will be.
much for your nice talk, and
Okay.
hope that we can meet at least in person
Yeah, yeah, sure.
at,
Huh,
at
definitely.
some
We'll
point.
definitely.
So, thank you very much.